Hi there, my name is Carlos and I'm a fourth year mechatronics engineering student.
And my name is Kwan. I too am a fourth year mechatronics engineering student. This year, our project is focused on SLS 3D printed compliant mechanisms and their applications in transtibial prosthetic sockets. We would like to start off by acknowledging the team over at the Creative Design and Additive Manufacturing Lab for making this project possible. Thank you to Professor Olaf Diegel for supervising the project, Dr. Jean Schut for providing continual guidance and feedback, and Ishan Singhal for supporting our project and discussing our designs with us. In New Zealand, 1 in every 1,000 people are amputees. It is also estimated that by 2050 there will be 3.6 million people in the United States living with limb loss. This number is dwarfed by the 25 million people who will also need prosthetic/orthotic devices in developing regions such as Asia, Africa, and Latin America by 2050. The number of amputees worldwide is on the rise, and technology has not kept up with the times. From our respective literature reviews, we have identified major problems with current prosthetic sockets. The current industry standard is non-compliant sockets made out of rigid materials such as carbon fiber, fiberglass, or polypropylene. While these materials are great at supporting the user's residual limb and thus the body, they cause unnatural movement when designed incorrectly, and due to the non-compliance may also lead to bad pressure distribution, especially when the residual limb volume changes over time. This leads to general discomfort at a minimum and may result in chafing, tissue damage, and more edema, which creates a cycle of further damage. Alongside the structural issues, there are also heating issues. Currently, the standard is to use fabric and silicone liners to help reduce chafing and movement within the socket. However, both the liners and socket are in essence insulators and lead to bad heat dissipation within the socket. This again results in discomfort, chafing/tissue damage, and further edema. Compliant mechanisms, while still young as a field of research, are becoming more and more promising with the advancement of rapid prototyping and manufacturing methods such as selectively laser-sintered 3D printing and advancements in materials such as PA2200, also known as polyamide 12. This presents an opportunity to investigate integrating the growing field of research into compliant mechanisms into the development of transtibial prosthetics. Because compliant mechanisms are inherently elastic, we plan to use this elastic behavior to create spring-like devices with passive return to enable a compliant passive socket. This would result in a more comfortable prosthetic that can adapt to the user rather than the user being forced to adapt to a rigid prosthetic socket. Through the application of SLS 3D printing, it may be possible to produce a custom and rapid solution designed specifically for each individual, saving both time and cost. To be able to implement these compliant mechanisms into prosthetics, we must first develop a library of mechanisms and a framework by which to test/classify them. This framework must also allow for rapid iteration, as it means many designs can be explored concurrently without waiting for a print to finish. We would now like to introduce our lab space where we print, process, and custom fabricate testing equipment for our compliant mechanisms. This is the EOS Formiga P110 Velocis. As you can see, it works through the deposition of the nylon PA2200 material onto the bed to form a layer. A laser then sinters the deposited layer, fusing the new material to the old structure. This, in essence, grows the structure out of the powder. One of the key benefits of this method of additive manufacturing is that it does not require support material, as the bed acts as a support. This, combined with the high accuracy and speed, mean that our complex geometries can be produced efficiently. However, like traditional 3D printers, a certain amount of post-processing is required. In this case, parts must be cleaned with compressed air to remove the excess nylon powder. The design of compliant mechanisms is not intuitive at first. From a traditional engineering standpoint, it is often looked down upon for things to bend or flex. This is because many systems in the engineering world are designed to be rigid in nature, such as the case with traditional transtibial prosthetic sockets. This meant we had to first learn to intuitively design compliant mechanisms, specifically ones which could be additively manufactured. From here, my partner and I aimed to develop a wide range of compliant mechanisms, which we then categorize into 3 types based on their motion and how they store energy. Axial. These compliant mechanisms can be thought of as typical linear springs. These mechanisms store energy in relation to displacement along an axis, and therefore also return on the axis. Traditional analogies are linear/nonlinear springs and leaf springs. Torsion. Torsional mechanisms store energy and deform through angular displacement, or in other words, through the rotation about an axis. Some traditional analogies are torsional springs and spiral torsional springs. Pathing. These refer to spring members who store energy based on a combination of linear and rotational displacements of axes, leading to seemingly changing paths. This type of compliant mechanism may also be thought of as translating the displacement direction of one member into another member moving in another direction. Some examples of this pathing mechanism are gripper-based mechanisms, which, when pulled, have members deform along a path and store energy along that path. Traditional analogies include linkage-based mechanisms and tools such as grippers or wire cutters. We also took to origami for inspiration to base some of our designs on. Origami is an ancient application of compliance where folds and creases act as compliant features. In particular, there is a branch of origami known as motion origami, which focuses on motion derived from crease geometry. This type of origami has seen extensive application in space technology due to its deployability between several stable configurations. Motion origami comes in spring-like forms where a restoring force resists motion away from the equilibrium position, as well as forms which show no passive return mechanism. While promising, origami patterns are designed around the properties of paper, namely zero-thickness folds and material that is extremely flexible. Translating motion origami patterns from paper to a 3D printed framework proved too complex and the idea was not pursued further. It was important to use the inbuilt SOLIDWORKS nonlinear simulator to validate the deformation and movement of the components before printing them. This is because the SLS process is expensive given the high machine cost, material cost, operator time, and post-processing time. The simulations serve twofold. Firstly, to ensure there were no major stress concentrations which would cause the part to fail under deformation unexpectedly, and secondly, to check to see if the deformation occurred as expected. The greatest problem with the simulations was the difficulty to simulate models in multiple degrees of freedom. Pathing and torsional mechanisms especially needed to be heavily constrained to produce useful results and in some cases failed to be simulated. After discussing these factors and results with our supervisors, we came to the conclusion that we should focus on axial type compliant mechanisms as they were the most promising for their application into a prosthetic socket. These simulations also served to be a model to compare to when doing our experimental designs/tests.
To create an effective testing method to ensure comparable data is collected, certain features are needed on the parts designed under the categories of axial, torsional, and path springs. These additions allow a single standard testing rig for each category of compliant mechanism. The testing rigs accommodate for a degree of automation in order to minimize human variations between tests. The automated element is implemented through the use of an Arduino board, a computer, and a camera, in this case, a phone. The Arduino board is used to automate the force applied to the testing part, while the camera records videos of the part so the deformation can be accurately determined, and the computer is used for data logging as well as processing. A testing rig was designed for axial and torsional mechanisms. However, only axial springs were needed to design a prosthetic socket. The test works by extending the compliant mechanism by using a servo motor connected to a spring with a known spring constant to apply an effective force on the part. The resulting extension of the axial spring is then tracked on video to calculate the effective spring constant of the parts being tested. After designing the testing rig, it was built from laser-cut acrylic with an etched scale on the surface to calibrate the video tracking software. The servo motor is connected to an Arduino with a serial connection to a computer so we can read from the serial port. The Arduino is programmed to run a servo motor with an encoder and send position data through the serial connection. This connection is monitored via a Python script which creates a spreadsheet as well as automatically logging the data sent via the Arduino. The script then allows a user to enter the axial spring extension values as they are analyzed from the corresponding video. By entering these values, the force exerted at each interval, as well as the respective displacement of the axial spring, is recorded in a CSV file with a descriptive title. Once all values are accounted for, the spreadsheet can be inspected and used to calculate the spring constant of the part tested. With this data collected, we then analyze it to determine the effective spring constant from each part by fitting a linear relationship. The data was collated into an Excel spreadsheet and then plotted on a graph. A linear fit was applied to the data, making the inverse of the gradient correspond to the spring constant of the part. The inverse is due to our independent variable being force and the dependent variable being extension, leading to a graph which is opposite to what would normally be seen in a force-extension relationship. There is some sign that the axial springs show nonlinear behavior at small deflections. However, with high R-squared values, we believe a linear fit of the whole range of deflection is justifiable. To test for factors affecting the properties of the spring, we tested for the thickness of the spring, the width of elastic members, and the internal geometry of the mechanisms. The testing parts were designed to vary these properties as a demonstration for the validity of this testing procedure. The factor found to be the most significant for varying the spring constant of the material is the width of the elastic component. Increasing the width of the elastic material from 0.6 mm to 1 mm resulted in a threefold increase in the effective spring constant of the part. Compare this to the thickness, where increasing the thickness from 8 mm to 12 mm only resulted in a twofold increase of the effective spring constant. To demonstrate and validate the procedure we developed, a prosthetic socket with axial springs for compliance was designed. We came up with two possible arrangements for the axial springs, a radial and a concentric arrangement. In the radial arrangement, the springs are essentially in parallel to each other, allowing for higher stiffness overall. The double layer created also allows for greater ventilation as well as protection for the soft inner components thanks to a harder, more durable exterior. The other design is one where the springs are arranged in a concentric manner around the socket exterior. Arranged this way, the springs are essentially connected in series to each other, allowing for lower overall stiffness. This design can allow for ventilation by removing material from the socket exterior while allowing for the structure to remain largely unaffected. These designs were refined and made better over time. Having said that, a testing procedure was not made for this overall design, so it could not be validated to the extent of making any conclusions from it. With a classification method and design framework for compliant mechanisms, we have created a standard approach for the otherwise open-ended and intuitive process of designing compliant mechanisms. While this approach definitely limits the potential for design of compliance, it also lowers the burden of designing new and creative designs so that compliance can be rapidly prototyped. This framework is also then compatible with a testing procedure to validate the corresponding classifications of compliant mechanisms and allow for the optimization of implementations, such as a compliant socket. From our own testing of compliant mechanisms, the necessary dimension changes to accommodate for the volumetric changes of residual limbs throughout the day can be achieved. However, the passive nature of the socket design also means external forces will deform the socket. An investigation into interface pressures on transtibial amputees showed a 17 kilopascal diurnal variation in interface pressure and a 99 kilopascal mean interface pressure. This shows pressure acting on the socket due to ambulation is approximately 6 times larger than the pressure exerted on the socket due to daily variations in residual limb volume. A passive socket designed to accommodate for changes in residual limb pressures cannot differentiate between external pressures and internal pressures. Thus, it is not feasible to create a completely passive compliant mechanism as a socket for transtibial prosthetic devices. There is room for future work on the development of an active compliance socket which can selectively accommodate internal pressure changes while providing suitable resistance to external pressure variations. This investigation focused mainly on axial compliant mechanisms, but if an active design approach is considered, path compliant mechanisms can be considered in greater detail. We believe that the framework we set out can be used for the initial stages of the development to fast-track the designs of compliant mechanisms. However, we also recommend that once the core concepts become intuitive to the person designing them, to abandon the framework so that their designs can become more specific to the task they are designing for.